Here we are looking at a simple formula for the inverse of a 2 by 2 matrix, as well as a nice easy test to help us determine if the inverse exists. So here we go. Here is the first big theorem of the section. Now to begin, we want to let matrix A be a 2 by 2 matrix defined as A, B, C, D. And this is such that A, B, C, and D are all scalars. Now, if the quantity A times D minus B times C does not equal 0, then matrix A is invertible or non-singular. And we define the inverse of matrix A as 1 by this quantity, A times D minus B times C, multiplied by the 2 by 2 matrix whose entries are D minus B minus C, A. And this will be such that the product of matrix A with the inverse of matrix A is equal to the 2 by 2 identity matrix, and that the product of the inverse of matrix A multiplied by matrix A is also equal to the 2 by 2 identity matrix. Now, if the quantity A times D minus B times C is equal to 0, we say that then matrix A is non-invertible or singular. So this quantity A times D minus B times C is called the determinant of matrix A. And this determinant of our matrix A is not only going to be important here with a 2 by 2 matrix, but it's going to continue to be important as we look at larger matrices. Now, we denote the determinant of matrix A as det of A. And for now, this is equal to scalar A times scalar D minus scalar B times scalar C. So quick conclusions or observations from this theorem for a 2 by 2 matrix A. So again, if the determinant of this 2 by 2 matrix A does not equal 0, then A is invertible. So in other words, A is non-singular, and the corresponding matrix equation will have one unique solution. Now, we're also observing here that if the determinant of matrix A is equal to 0, then matrix A is non-invertible or singular. So if matrix A is non-invertible, this lets us know that the corresponding matrix equation is going to have infinitely many possible solutions. Now, before we go ahead and look at examples of both of these cases, we need to verify that this formula, this 2 by 2 formula for the inverse above, is in fact holding true. So here we go. We want to verify that 2 by 2 inverse formula that is given to us with this theorem. So to begin, let's let matrix A be a 2 by 2 matrix defined by the components A, B, C, D. And this, of course, is such that A, B, C, and D are scalars. Now, what is our goal? What is it that we want to show or confirm? So our goal is that we want to verify this inverse formula. We want to verify that the inverse of matrix A being equal to 1 over the determinant of the original matrix A multiplied by the 2 by 2 matrix D minus B minus C A is in fact the inverse formula. So that's our goal. We want to verify that this formula is in fact the inverse of matrix A. So, in other words, we need to show that. Two things. We need to show that matrix A multiplied by this inverse is equal to the 2 by 2 identity matrix. And since matrix multiplication is not in general commutative, we also need to show that the reverse holds true, that the inverse, this inverse formula, multiplied by matrix A is also equal to that 2 by 2 identity matrix. So in order for this formula to be true, both cases must hold. So let's think about case 1 here. Case 1. We want to show that this beautiful 2 by 2 matrix A multiplied by this inverse formula is going to produce the 2 by 2 identity matrix. So before we even get started here, we should make a note that this is all under the assumption that this determinant of matrix A is not equal to 0. Now, it's pretty easy to see why this determinant cannot be equal to 0 if we look at the formula. What would happen if the determinant was 0? We would have 0 in the denominator, which we of course know is nonsense. It's impossible. You can't have it. So in order for the inverse to exist, this determinant, this quantity must be non-zero. So with that in mind, let's proceed. So we, again, are taking this beautiful 2 by 2 matrix A and multiplying it by this given inverse formula. So we have matrix A defined as A, B, C, D multiplied by 1 over the determinant of matrix A, so that's a scalar, multiplied by the 2 by 2 matrix D minus B minus C, A. And now, by matrix multiplication, by those properties, recall that the order of the scalar doesn't matter. So what I'm going to do to make our computation a little bit easier is to just pull that scalar 1 by the determinant of A to the front. So we have 1 over the determinant of A multiplied by that 2 by 2 matrix, ABCD, multiplied by that 2 by 2 matrix, D minus B minus C, A. So these mean the same thing. But with the second form, it's going to be a tiny bit easier to simply start by finding the product of these two matrices and then distributing the scalar through. So that's how we're going to proceed here. Let's find the matrix product, or compute the matrix product. So we are taking just the product of these two 2 by 2 matrices, and we can expand this by either the row column rule for computation, or you could use your formal definition. I leave that up to you. Pick your favorite method. So I'm going to use the row column rule here. So multiplying the first row of the first matrix by the first column, we have A times D plus minus B times C. And the first row, second column will be A times minus B, so we have a minus AB plus B times A. Beautiful. So moving to the second row, first column, we have C times D plus D times negative C, or minus CD. And last but not least, second row, second column, we have C times negative B, or minus BC, plus scalar D times scalar A. Beautiful. And again, that was by the row column rule for matrix multiplication. And look at this beautiful cancellation. We have minus AB plus AB goes to 0. And then we have CD minus CD also goes to 0. So we are left with the 2 by 2 matrix. We have AD minus BC, 0, 0, AD minus BC. So Now that we have computed our matrix multiplication, we are officially ready to multiply by the scalar, defined as 1 over the determinant of matrix A. So here we go. We want to scalar multiply this product by 1 over the determinant of matrix A. And we are hoping that this is going to leave us with the identity matrix. So here we go. We have, again, 1 by the determinant of matrix A, and we are multiplying this scalar by the original product. So let's convert that determinant of matrix A. We know that this quantity is defined as A times D minus B times C, and we're taking that 2 by 2 matrix that we just found above and multiplying, or scalar multiplying it by the determinant, or 1 over the determinant. So we can say by properties of scalar multiplication, we can distribute this scalar through to each term. So we're left here with AD minus BC divided by AD minus BC. And now 0 divided by this scalar is just 0. And again, 0 divided by this scalar is 0. And then the last entry is AD minus BC all over AD minus BC. And look at all this beautiful cancellation. We see the entry in the first row, first column, cancels to 1, and the entry in the second row, second column, also cancels to 1, leaving us with that 2 by 2 matrix, 1, 0, 0, 1, which is the identity matrix, the 2 by 2 identity matrix. Woohoo! And so we have exactly what we wanted to show. We have shown that matrix A multiplied by this inverse formula is, in fact, equal to that 2 by 2 identity matrix. Now, we're not done yet. This is only one direction. So I want you to note that we still need to show case 2. We still need to show that the inverse formula multiplied by matrix A is also equal to the 2 by 2 identity matrix. Now, the process for case 2 is exactly the same as what we've shown above, with the exception of computing the matrix product. We'll simply need to switch the order here. But other than that one minor change, again, the process is the same. So I'm going to challenge you and leave this second case up to you. So good luck, take your time, have fun.